Today I'm going to talk to you about the work that GE has done to improve the state of software integrity. When we protect our industrial environments, we focus on availability, integrity, and confidentiality to protect our systems. The systems must always be available. They must operate with a high degree of consistency, and we must protect the information of our customers. When you think about it, integrity is not a really interesting concept on the surface. In fact, it's kind of boring. I think about software integrity like a great pitcher's duel. It's something you have to appreciate in context. Great pitching wins championships, and good software integrity programs protect our manufacturers, our operators, and our customers. In the AIC model, I'm here to tell you that software integrity is more than just a middle child. Trust in our environments often assumes the integrity of the hardware and software involved. We think about things like electronic security perimeters, and we neglect the assets operating inside those perimeters. In my prior work as a security architect, I would regularly focus on a network topology and the flows between components. I would completely ignore that the hardware and even the firmware involved could be invulnerable, could have issues. This was a fatal mistake. If you think about the types of incidents we've seen in the past few years, both hypothetical and real, what would software integrity have done to prevent those incidents from happening? Now, at the same time, our customers expect software integrity as a table stakes capability. When customers purchase a GE Mark 6E controller, they expect that our engineers have put the time in to properly apply software integrity to both the firmware and the operating system of that controller. At the same time, regulators are now issuing guidance in this space. I've got a few examples. NIST has specifically written guidance around how code signing should be performed, including algorithms, key lengths, and a number of other requirements. The FDA has created a software pre-certification program in order to speed the delivery of healthcare software into the hands of doctors and patients, but it requires demonstration of software integrity as a part of the delivery of that software. You're all probably familiar with NERC-CIP, which includes a specific requirement about how to demonstrate software integrity. Finally, the FAA has released an order that specifically includes language on how aircraft software must demonstrate integrity before it's transferred to an airframe. I'm here to tell you that software integrity is an area that's growing, and it's an area where I think that we can do better. So why does GE care about software integrity? The answer is in the pictures you see before you. As we move, power, and cure the world, everything that we do is powered by software. In order to deliver on our commitments to our customers, we must have software integrity. And on a personal note, software integrity means a great deal to me as well. When my first son, Cooper, was born, he used the GE fetal heart monitor during the delivery process. And now, as my wife and I plan to bring a second child into the world, we expect the GE fetal monitor to play another significant role in that process. I know the team behind that product, and I believe in the work that they've put into software integrity in order to provide that essential capability to patients. So how do we fix this? The answer is we focus on the pain. Using code signing and other cryptographic capabilities is painful. Human beings naturally avoid pain, and software developers, as a particularly smart breed of human being, avoid painful experiences. There are three main painful areas involved with industrial code signing. And I'd like to paint a picture for you along the lines of the theme of S4 about what would be possible if we solve this pain. The first issue is long life support. Keys, certificates, and the HSM platforms that store them expire well before the products in the field are retired. This causes a great deal of issue with our operators and consumers in the field. What if those keys, those certificates, the storage media were able to be rotated in a transparent way that enabled those devices to operate without interruption? The second pain point is build integration. I'd like to make a quick public service announcement. Please do not store your private keys on your build servers or in GitHub or anywhere else, really. If you don't do that, instead you're forced to rely on painful integration involving thick clients and static IPs. And frankly, that is a cloud anti-pattern. It waves in the face of the way that software development is headed. What if that was no longer a constraint? What if integrating with a code signing platform was easy? What if it worked like the internet and it just worked? The third pain point is verification in the field. We rely on third parties to verify the integrity of our software. I believe that's something we can solve for as well. At the end of the day, the concepts behind the public ledger are around using clever code and cryptography to create trust. What we decided to do was to use that same approach of clever code and cryptography to create a painkiller. And I'll show you an example of how that works. So, keeping in mind the pain points I just described, the first area to focus on is the big black box labeled HSM. And there's a reason that it's a black box. As a development team, as an engineering team, you shouldn't have to worry about which HSM you're on, where that's located in the world, what partition your keys are stored on, or what slot number you're having to deal with. Those are all painful experiences. They end up being tracked in spreadsheets. We can do better than that. By creating the signing service layer between the signing host and the HSM, we can enable the rotation and migration of cryptographic keys so that the user doesn't have to worry about where those keys are stored. Now, if you need to demonstrate to your auditor or your regulator where those keys are and that we're handling them with due care, we can do that. But at the end of the day, you should worry about, I have a key, it's named this, and I can reach it by accessing this URL. The second pain point is around integration. Modern development uses continuous integration and continuous development. We built a platform that integrates with Jenkins, and I'll show you an example of that output in just a moment. Developers should be able to configure their Jenkins build to consume cryptographic material, and the builds are signed. It should just work. It should take less than 30 minutes. So here's that example I mentioned. This is our painkiller in action. In step one, the first section of code that I've highlighted, you can see they're calling out to a signing service. They're using the Java jar signer utility, which signs the manifest, the files included in that jar file. It specifies an algorithm type, a key length, and then provides the PIN code associated with accessing that key. In the second highlighted code block, you can see that we're using that same jar signer utility to perform verification, the most important part. You can see that using the public key provided with that same jar signer utility, we're verifying that the manifest was signed by digital.ge.com. So that's all well and good. Those are pain points 1 and 2. But what about point 3? That's the reason I think we're all here today. Sometimes I feel like I'm the conductor of a hype train, and I'm doing my best to slow that train down rather than speed it up. So let's talk about this concept of certificate transparency that underlies our approach to pain point number 3. CT originated in RFC 6962 and was published by 3 Google researchers in 2012. It was focused on SSL and TLS trust and made it impossible for a certificate to be issued for a domain without the domain owner knowing it. This was later extended into the concept of binary transparency, or BT, which is what we'll be focusing on for the rest of the talk. The core components of the CT technology includes logs, monitors, and auditors. Logs are services that maintain crypto-assured, publicly auditable, and append-only records. Monitors are public servers that are periodically contacting all of the logs in order to verify cryptographic consistency. We'll walk through how they do that in just a moment. Auditors use lightweight software to verify the logs are behaving correctly and that a particular certificate appears in the log. This is essential for a client as it's verifying a binary to make sure that that certificate is present in the BT log. BT uses this CT technology to verify and track the hashes of binary files. So let's go deep. We're going to walk through a couple examples around hash trees and trust proofs. The trees you can see on the page before you are Merkle hash trees. They're cryptographically calculated trees where each node is a hash value that is the product of the child nodes beneath it. We're going to talk about it in concept of the tree on the left and the tree on the right. So first, let's talk through the consistency proof. A consistency proof verifies that two versions of a tree are consistent. If you have one version of a tree, other people have committed additional certificates to the tree, you now must verify that the tree is still intact. This is the function of a monitor. So walking through a consistency proof, we're going to calculate the root nodes of the tree in order to guarantee that the tree has only been modified in contractually verified ways. So in the example on the left, we'll use nodes I and j to calculate the root of that hash tree. Using node I and j combined with the new node k created by the product of the appended certificates, we can calculate the root of the new tree. If the calculated root of the new tree matches what's hosted by the tree, we can ensure that yes, the appended certificates were added correctly and the trees are true derivatives of each other. So using node I and j to calculate node m, and combining that with new node k, we can calculate the new root and verify that those two trees are cryptographically consistent. Similarly, when we perform an audit or inclusion proof, we're verifying that a certificate and its leaf hash are present in the tree. We're going to focus on the tree on the right in this example. Using certificate D3 as an example, we would have in our hands the leaf node D. Using the nodes I, C, and K, we can calculate the root of the new tree. If we can compare that calculated value with the value advertised by binary transparency, we can verify that that certificate must be present in the tree. Using nodes C and D, we calculate node J. Using I and J, we calculate again node M. Using M and K, we calculate the root of the tree. If that calculated root matches the value advertised by the binary transparency log, we know that certificate D3 must be present. So let's talk about why code signing and BT need each other. They're stronger together than they are apart. Code signing alone is not enough due to the risk of CA compromise. Now, I'm not here to talk about individual CA incidents or how that's trended over time. I'll leave that to you guys to go check out on your own. But I think it's safe to say that it's an issue we should all be aware of. Since the initial certificate transparency publication, security researchers have found improper CA issuance of certificates. There's a fantastic Ars Technica write-up. If you're watching this on video, pause the video and go look it up. The current CT logs are all separate and published by each CA. They're a series of islands of trust, as opposed to an interconnected distributed chain of trust. By the same token, BT needs signing to be effective. BT is a detection mechanism. That's great. It's more than we have in that space today. But it's not prevention. Combined with code signing, where you can integrate verification into the operating systems of our products, you can prevent improper software from being executed. At the same time, certificates are necessary for signers to perform revocation using PKI infrastructures we know and love. So how did we approach this? We chose to implement BT by leveraging these same CT principles I've described and the mechanisms to publish binary installable package information. Now, we're not alone in trying to attempt this. Google, Mozilla, and Cornell have all been exploring this concept in the past 12 months. What we did is we built a proof of concept for publishing and verifying. It leverages some great work by Google and their generalized transparency platform called Trillion, and enables contributions to a ledger using a really clever technique that the Firefox team has created. I'll walk through that in more detail in just a moment. We've built consumable verification software that can be used on devices in the field. Now, if you want to see this live, find us later for a demo, or if you're interested in the source code, we'd be happy to show it to you. So let's walk through a proof of concept. I'm excited for your questions at the end and the feedback on what I'm going to show you. So in order to add a hash to a CT log, there are 4 steps. First, you're going to create a hash value as part of your build process. Then you'll generate a certificate. You'll upload that certificate to the CT log, and finally, you'll be returned a leaf hash with a secure certificate timestamp for use in further verification. So on the screen, you can see step 1. As part of our build process, a script you could easily add to your same Jenkins build, we're generating a hash value of the binary we've just created. In step 2, we're creating a generic SSL certificate, the same type of SSL certificate you'll use for browsing. But we're doing something special. We're borrowing from Firefox's technique, and we're taking that hash value and splitting it into 2 component parts. Those become the first 2 elements of a domain name that is stored in that certificate. You'll see that again here in the verification process. Next, we'll upload that certificate to the log. It will add a new chain to the Merkle hash tree, consisting of a single certificate. Finally, the BT log will return a leaf hash and a secure certificate timestamp, which we'll use in verification. Those are essential to be provided to the consumers of the software. So now we'll move to the second piece, the more complex piece, which is verifying a hash is present in a BT log. This includes 6 steps: creating a hash from a binary you have in hand, acquiring the leaf hash that I described in the previous step, running an inclusion proof to verify that it must be present in the binary transparency log, pulling down the certificate information that we created in the previous step, identifying that hash domain containing that bifurcated hash value, and then verifying that hash value that we've calculated with the value that's present in the tree. So in step 1, we are calculating a hash using the same approach as in the build process, but this is with the local binary that we've been provided by our software manufacturer. In step 2, we'll acquire the leaf hash. There's multiple ways that this could be accomplished. It could be printed on paper, it could be issued via USB or CD, or to fully automate the process, it could be published on the internet in order to be automatically consumed by web services. We'll next run an inclusion proof using that leaf hash, which will follow the same process we walked through a few minutes ago, in order to verify that that certificate must be present in the tree. Once we've verified that, we'll pull down the certificate information. And included in that certificate, in the subject alternative name, is the same DNS entry that we looked at when we created it. Finally, we'll use that hash value, which was embedded in the certificate, which was guaranteed to be present in the tree, and we'll compare that to the same hash we've already calculated locally. If those 2 hash values match, the binary is in the same state as it was when it was built. So let's revisit the pain points. By combining the approach to code signing and to binary transparency, we can address all of the developer pain points. Long life support is solved by the code signing platform I described. Build integration is solved by the code signing platform I described. Verification in the field will be solved by the implementation of BT. So how are we making this real at GE? We're continuing to integrate BT with code signing. Today, those are 2 separate pieces of software. There's no reason why they can't be one, or at a minimum, complementary. The same certificate that's being published to the BT log could be used for a public key in order to perform verification. We can combine those 2 processes. We're also working to build an internal standard for submissions so that developers and engineers at GE can contribute to a BT log. We're standing up a public ledger for GE products so that all of you can check our work. We're also adding BT verification into GE products and into standard software integrity tools. Again, take away the developer's pain. So how can you help? I think we're stronger as a community than we are as a series of individuals. You can help by contributing your input to a unified standard for BT. There are many places that we could do this. There are working groups. There are consortiums that we could develop. We'd love for ideas and partners to help us make this a reality. You can also volunteer to host part of a distributed ledger among many software providers. Just GE hosting a ledger is great, but every industrial software provider hosting a distributed ledger means that we're trusting each other. We're providing trust as a community. You can also help us evaluate adding more software information into this ledger. We can create a policy-based software verification process against a unified ledger. We've got some ideas, but there's many more things that could be added. You could include end-of-life information to advertise that and publish that to a log. You could include security assessment data. You could also include bill of materials data and dependencies. So that's all included as an immutable public record. You can also help by building BT checks into open source software integrity tools. Again, we're stronger as a community. I'd like to also acknowledge the CT pioneers at Google and the Trillion Project. They've led the way with some fantastic research. Mozilla and the Firefox team came up with a really clever way of using those SSL certificates, and they deserve total credit for that. The Contour project at Cornell was a great example of an attempt at a practical BT implementation. And most importantly, our teammates at GE in product security and global research that took this from a crazy idea to something that we believe will change the industry. Thank you very much for your time, and I'm excited to hear your questions.
All right, good morning, everybody. I'm Jason Holcomb with Revolutionary Security. I'll be moderating the session and helping field questions here. Thank you, Clay. Great presentation. What questions do we have in the audience?
Hi, Tim Deerking at Aclara. Question I would have is, how do you verify the authenticity of the code and the signer when it's submitted into the process? And then a follow-up is there any ability to revoke trust in something that was once trusted?
Those are great questions. Thank you for those. I neglected to mention that. So the way that submission to the BT log works is you must be rooted to a CA that is trusted by the BT log. So there's a backbone of PKI that lives underneath that process. There's a contract of submission requirements that are necessary. And that's built, again, on PKI infrastructure and cryptography. In order for revocation, yes, the answer is yes. So it's an immutable append-only log. So you will never remove certificates from the tree, but you can declare those certificates to be invalid or compromised or some other status.
All right, very good. Any other questions? All right, if there are no other questions, I had just one quick one for you, Clay. From members in the room who maybe aren't on the product development side of this, but maybe are on an asset owner side, what should they be thinking about in terms of either asking from their vendors or what contribution do you expect from the asset owner community to help drive this kind of effort forward?
Yeah, that's a great question. I think the strongest argument for pushing the boundaries of software integrity comes from our customers. The regulators are kind of a stick that we get beaten with occasionally. But the most incentivized way for us to modify our products and to push the boundaries, again, of software integrity, to make sure that the firmware, the operating systems, the applications we provide to you have a high degree of integrity, is for the customers to ask for it and to tell us that they expect it, and that without it, they might not buy our products. So as an operator community, you can help us push those boundaries.